Hey, have you ever stopped to wonder why some things just spread out into a puddle while others hold their shape perfectly? Today, we're going to dive into the secret science that governs everything from the toothpaste on your brush to, well, the buildings we live in. It's this hidden force that's absolutely everywhere, and we're about to pull back the curtain on how it all works.
All right, so let's kick things off with a super simple everyday puzzle. Why does honey just ooze into a puddle, but a lump of dough, well, it just sits there, right? It holds its form. I mean, they're both soft, squishy materials, but they act completely differently. The answer? It lies in this really fascinating field of science.
So you've got these two extremes, right? On one end, you have stuff like honey. We call that viscous. It flows super easily and couldn't care less about holding a shape. Then, on the other end of the spectrum, you've got elastic materials, like a rubber band, which fight against being stretched and snap right back. But the really cool stuff, the secret to our dough, happens somewhere in the middle, in that space between those two.
Right, so that sweet spot between flowing and holding firm, well, there's a whole science that governs that, and understanding it, that's the key to unlocking how we design and control pretty much the entire physical world around us.
And that science is called rheology. Simple as that. It's the study of how materials flow and, deform. And look, it's not just about watching things ooze around. It's about taking active control, making a material spread out perfectly, hold its shape, or even collapse exactly when we want it to.
Okay, so what this boils down to are three key behaviors. You've got your purely viscous materials, like our friend the honey. Then you have the purely elastic, like rubber. And then you have the superstar of shape control, the viscoelastic materials. That's our dough. It's this perfect mix of both properties that lets it flow when we need it to, but then hold its shape when we tell it to stop. Pretty cool, huh?
Okay, so we get these core properties, but how do we actually use them? Well, it turns out engineers have this amazing toolkit that lets them precisely control how a material behaves.
And this is where the science really becomes an art form. See, these aren't just random, passive properties of a material. Think of them more like levers you can pull or dials you can turn to get the exact behavior you're looking for. It's all about commanding the material to do what you want.
Now, one of the most important tools in this whole kit is something called yield stress. And honestly, the best way to get this is to just think about a bottle of ketchup. You know how it just sits in the bottle, kind of like a solid, but then you shake it or you squeeze it hard enough, you're applying stress, and bam, it suddenly starts to flow like a liquid. That moment, that hard enough point, that's the yield stress.
The whole process is actually pretty simple, but it's incredibly powerful. First, you apply some force, but the material just holds its shape. Then, as you ramp up that force, you hit that magic threshold, the yield stress point. And finally, the material's internal structure just kind of gives way, and it starts to flow. This level of control is absolutely critical for stuff like 3D printing, right? You need the material to flow out of a tiny nozzle, but then you need it to set and become solid, like instantly.
But hey, yield stress is just one tool in the box. Engineers also play with a material's viscosity, its thickness. They use this wild property called thixotropy. That's the reason paint flows so smoothly when you brush it on, but then thickens right up so it doesn't just drip down the wall. And of course, they tweak the elastic modulus, which is basically the material's springiness, to make sure it holds its final shape perfectly.
So engineers have this incredible toolkit at their disposal. But I want to be clear, this isn't just some abstract lab theory. These tools are being used right now, every single day, to invisibly shape the world all around us. No, seriously, once you know what to look for, you'll start seeing it everywhere. Rheology is like the invisible engineer making sure your yogurt has that perfect creamy texture, that your concrete flows into place without a problem, and that the plastics in your car are molded without a single flaw.
I mean, the sheer range of this science is just incredible. In the world of polymers, it's what guarantees your phone case is molded perfectly. In the food industry, it's the secret behind the texture of your favorite yogurt or that satisfying snap of a good chocolate bar. But it's also at the absolute cutting edge of medicine. It's being used to build these amazing scaffolds for growing new human tissues and to make sure 3D printed biomaterials can hold their incredibly complex shapes. We're talking about new frontiers in healthcare, all thanks to this science.
But controlling all these properties, it's not as simple as just cranking a dial up to 10. Real success is found in a perfect and often really delicate balancing act. Yeah, getting a material to behave exactly how you want, it's like this delicate, high-stakes dance. You need it to flow just enough to get into the right shape, but then you immediately need it to be stable enough to stay in that shape. It's a constant game of trade-offs.
And this really gets to the core of the challenge. If your viscosity is too low, well, it's like trying to build a sandcastle with water. The whole structure just collapses into a puddle. But if your viscosity is too high, it's like trying to pour a brick. The material won't flow, it won't fill the mold, and you're left with a useless, incomplete product.
And just to make things a little bit trickier, there are always other factors in the mix. Temperature, for one, can change everything. Just think about how butter softens in the sun. And when you're working with polymers, little inconsistencies in the length of the molecular chains, something called polydispersity, can lead to all sorts of unpredictable and really challenging behaviors.
But in the end, it really all comes down to this one simple idea. Rheology and shape control, it's all about that fundamental balance between flow and stability. It's a material's ability to take a shape and its strength to hold on to it. So now that you've had a peek behind the curtain at this invisible science of shape, what are you going to notice differently? Maybe the way paint clings to a wall, or how your food holds its form on your plate, or even the super precise lines of a 3D printed object. The secret science of shape, it's absolutely everywhere.